All right, so the last chapter was sort of just a primer on coordination chemistry in general, different nomenclature, isomers that can exist, different ligands, what is coordination chemistry. Now we're going to dive in specifically to D metal complexes. And coordination chemistry is sort of a bigger umbrella. Now we're just going into the transition metals during chapter 6. And so the transition metals are very interesting, many different oxidation states, many different geometries that can't be explained by VSEPR. So, why, for instance, do we have a nickel chloride complex that is tetrahedral, but a palladium complex that is square planar? Palladium, if you look on the periodic table, is right below nickel on the periodic table. So they're in the same family, same number of d electrons, same oxidation states of 2 here, different geometries. One of them is a VSPR geometry, one of them is not. Some other interesting cases, this tungsten complex is trigonal prismatic, not octahedral at all. You have some interesting 9-coordinate systems like this one here, or just a lot of variability here. 5-coordinate systems, here's a stable trigonal bipyramidal complex, which is the VSEPR geometry, but here is a square pyramidal 5-coordinate complex. So, what we're going to explore in this chapter in part is, what gives rise to this structural diversity and how can we predict it? Okay. It's the d orbitals that make a difference. And so when we look at the main group compounds, the bonding is dominated by s and p orbitals, pretty much exclusively. It's been a actually hotly debated topic in chemistry for quite some time, but I think within the last 2 decades, it's mostly been settled that d orbitals, empty d orbitals even, don't play any role in main group chemistry. So even if you have a phosphorus, which has some empty 3d orbitals, for example, early on people were thinking, even up to kind of recently, people were thinking maybe you could have some chemistry happening in those empty d orbitals. Turns out that's not true. So yeah, because you're only dealing with S and P orbitals, the octet rule works fairly well to protect stability. That's why VSEPR works pretty well. And you have pretty strong bonds because you have S and P orbitals. You have good overlap. And this gives rise to big differences in energy, relatively speaking, in the different molecular orbitals. So if you look at your HOMO-LUMO gap, that's the highest occupied molecular orbital that has electrons in it, versus the lowest unoccupied molecular orbital that doesn't have electrons in it. If you look at that gap, that's usually in the ultraviolet, okay? And so as a result, most main group compounds and organic compounds, for example, are colorless. They're absorbing in the ultraviolet, and they're not going to have, they're not absorbing visible light. So the absorption of visible light, is the main mechanism for giving color to chemicals. So that's why they're colorless. This is what kind of attracts a lot of people, myself included, to inorganic chemistry, is the beautiful colors. And sort of, I'm not going to use the word mystery, but the allure of those different colors, where they come from. It is known. We're not going to go too deeply into color in this course, but it's very well known. The theory's a little bit complex, but it's well known and established what gives rise to all the different colors. Okay. But yeah, so in transition metals, you have d orbitals now participating in the bonding. So because you have d orbitals, the octet rule doesn't work anymore. You have more electrons. There is a kind of an equivalent of the octet rule we'll talk about, but it's not super great at predicting. It's called the 18 electron rule because, well, you have 8 electrons in the s and p to get to the valence state plus the 10 d electrons, right? So that's a total of 18. But yeah, you're going to have a visible HOMO-LUMO gap because you have these weaker bonding and anti-bonding interactions from the d orbitals being involved in the bonding. There's just less overlap. And so that gives rise to all these different colors. Okay. So talking about colors, we're talking about the valence electronic transitions molecules. It's due to absorption. Got to know your art. You got to know your color wheel, right? And so you may know that things opposite of the color wheel are called complementary colors. And this is a very simple way. If you have like one peak in a UV vis spectrum, you can predict what its color is. So if you're absorbing light, if you're absorbing some violet light, okay, your compound is going to be yellow. If you're absorbing green light, your compound is going to be red. If you're absorbing colorless, absorbing ultraviolet light or infrared light only, your compound is going to be colorless because you can't see that. Maybe some other animals with different types of eyes can see ultraviolet and infrared. That is indeed true. For example, it's well known that pigeons, for example, can navigate with by using ultraviolet light. So quite interesting. Yeah, wide variety in colors. You can see here some different metal aqua complexes going across the periodic table. Scandium is colorless. You can see it's chromium-3 compound. Beautiful different colors for depending on the d electron count. And here are just different isomers, right? Or similar complexes. All of these are cobalt-3 complexes with different amounts of amine ligands. So you put in some chloride in there, or you change the stoichiometry, you get these different colors. So quite interesting, very diverse. The electronics of this get pretty complicated to explain these colors, like I said. But there are still a lot of different things that in this chapter we're going to talk about in terms of bonding and predicting molecular structure and reactivity.